Hi, I'm Professor David Farina. In today's lecture, we're going to be discussing light and matter and how it's connected to the inner workings of our cosmos. Specifically, we're going to be talking about the Doppler effect. Let's get started. What is the Doppler effect? Well, the Doppler effect is something that you probably have heard yourself with sound waves. So if you've ever heard that the frequency of a car changes, or the pitch of a car changes as it's approaching you compared to as it's leaving you, maybe you'll hear something like that sound is the Doppler effect in action. Now, the Doppler effect is going to be possible with any type of wave, including light waves, which is what we're going to be focusing on mostly today. Now, with light, it's a lot harder to see the Doppler effect in our everyday lives because the Doppler effect is a much, much smaller change when you're dealing with light speed. With sound waves moving just over 700 miles per hour, the effect of a few miles per hour is quite a big ratio compared to its top speed of 700 plus miles per hour. Whereas with light traveling at 300,000 kilometers per second, or 7.5 times around the Earth, being able to see a Doppler effect is almost impossible, except for with our detectors, our cameras, where we can actually measure light to a much higher degree than we can with our eyes. When we look at an object that's in motion, we can see that if the object is leaving us, it will have an apparent red shift as a result. And if the object is moving towards us, then we will see an effective blue shift. The light will literally look more red or more blue than it should look. And this has to do with the motion of the objects. If the object is stationary, like in this top diagram, notice that the waves of light, the timing of those waves is going to be a consistent value. When we have an object that's moving, here's 1, 2, 3, and 4, the wave fronts from these are compressed in the direction as the objects are moving toward it. As the objects are moving away, the wavelengths are being elongated. So remember, red light, longer wavelength, red shift. Blue light, shorter wavelengths, blue shift. I really highly recommend you play around with this Doppler effect animation that I'm going to put in the links below, because I think it'll really help you understand how this process works. Now, the Doppler effect equation, it might seem daunting, but it's actually pretty easy if you think about it. So I'm going to work you through this today. So as it says here, we've got the actual wavelength emitted by a source. So here's the wavelength, that's the symbol for wavelength, lambda. And this is simply the naught or 0 mark. So we've got the actual wavelength with no motion. And then we have a second part of our equation, the delta lambda, or the change in wavelength. This simply means the change in, and then this wavelength symbol. So the wavelength change due to the Doppler effect is what we want to know. So if the change is in the numerator, the actual value is in the denominator, this is directly related to the velocity of the object or source divided by the speed of light. So the velocity, or radial velocity, I should say, of the object is divided by the speed of light. So this equation is not really all that challenging if you really break it down. Now, what we mean by radial velocity is that, for example, The Doppler effect is used when police are using radar. And what they are getting for a value is your speed, your velocity, how fast are you going. But they're not truly getting your maximum velocity. They're getting a component of your velocity. Let me explain. First, notice how the cop car here is at an angle compared to you. You're driving down the road, and this is your speed, v. What the cop is able to measure, however, has a limiting factor based on his angle. And what he measures is v sub r, your radial velocity. Now notice that this is the hypotenuse of the triangle that's formed by VR and an imaginary line like this, perpendicular to VR. So what we should know about a hypotenuse of a triangle is that it is always longer. In other words, you're going faster than that police officer can measure. So next time you get pulled over and the police say that you were speeding, you might not want to tell them that they were only able to measure your radial velocity because, well, you were actually going faster than they measured. The same thing can be said about our ability to measure a star's magnitude of its velocity. We are only able to measure the radial velocity of a star. If the star is on some other angle other than directly away from us, we can only get a minimum velocity. How fast is its radial velocity, not its actual velocity. So what this means is that the universe doesn't always play nice. We need to have the ability to understand how these things work and interpret our bounds. In other words, there's some error involved, and we need to understand how much error is within our measurements. And we need to be very clear as scientists when we have error, potentially, where it's coming from. And this would be one of those examples. Now, going back to spectral lines, the broadening of spectral lines can happen as a result of the Doppler effect. So Doppler broadening is that in principle an absorption or emission line should be a single frequency. But what we find is that they're not a single frequency. They are wider than that. And the reason that they're broadened has to do with the Doppler effect. Because remember, atoms are moving in random motions. And so because they're moving in random motions within a substance, we're going to get some of them that are moving farther away from us, causing them to be redshifted. Some of them are going to be moving towards us, causing them to be more blue shifted. And so from the perspective of an observer with our telescopes here on Earth, we don't see just one single line like you would in a laboratory. You would see things going in all directions. So on the one side of the spectrum, you can see it's blue shifted. And on the other side of the spectrum, things that are moving away from us are red shifted. So a second effect here, it's kind of the same effect, but it's another component to this, is that the higher the temperature of an object, the broader its absorption and emission lines will be, right? Because consider this. What is temperature? Temperature is the average kinetic energy of particles in motion. Kinetic energy is speed or velocity. So if we're moving faster, it should make sense that they have a wider Doppler effect, right? They're moving away faster, or they're moving closer towards us faster. So hopefully this helps you understand the Doppler effect. Definitely make sure that you click on that little animation in the links below. If you like this video and you'd like to learn more about astronomy, please click like and subscribe below. If you'd like to get a notification every time I make a video, please click that little bell at the bottom as well. Thank you, and I hope you have a stellar rest of your day.